Hello, we're going to go over how to make a confidence interval for a population mean when we do not know our population standard deviation. So here's an example of a problem that you might run into. Notice that we still have a sample, got a sample of 25 adult men. We have a sample mean, 186, so X bar is 186. And we do have a standard deviation, but this is not a population standard deviation. And you are asked to construct a 95% confidence interval. So we're still looking for an interval that contains our population mean. Because this standard deviation is not a population standard deviation, I cannot use the formula that I've been using. Now, how do I know it's not a population standard deviation? Well, for one, the word population is not listed there. It does not say population standard deviation. Secondly, grammatically speaking, the phrase with a standard deviation of 12 indicates that that standard deviation belongs to the sample. So we can still find this interval, but we can't use our standard normal distribution. We can't use z-scores. We also can't calculate this standard deviation of X bar because we don't know our population standard deviation. But we can use what's called the t-distribution, sometimes called the student's distribution. It's very similar to our z-scores, but we'll be finding t-scores instead. Now, there's 3 times that you're going to be using t. And in all 3 cases, our standard deviation is unknown. Our standard deviation for our population is unknown. So the sample size doesn't come into play, and neither does the shape of our population. T-distributions are similar to normal distributions. They're both bell-shaped. The area under the curve is 1 in each case, and the mean, that tallest point, has a value at 0. It's just in the t-distribution, it's a t value at 0, and over here in the z-distribution, it has a z value of 0. Our standard deviations are different. Standard deviation under a normal distribution has a value of 1, but standard deviation in a t-distribution varies. And it depends on something called DF, which stands for degrees of freedom. You will never have to use this formula to calculate that degrees of freedom, so don't worry about that. In general, our t intervals are greater than our z intervals because t values are larger than z values generally for the same amount of area. So to find this t-score, we only need what's called the degrees of freedom, and that's this df right here. df depends on the sample size n minus 1. If you really want to know what df stands for, ask me on the next Zoom meeting, and I will explain that to you. So here's how this works. You're going to use Desmos, or you're going to use your TI-84, either the calculator or the app. And what we're looking for here is the area in the right tail. And we know what the degrees of freedom is. Remember, degrees of freedom is the sample size minus 1. So if you're using Desmos, follow those directions. If you're using the TI-84 app or calculator, follow those directions. And what you should see in both cases is that you have a t-value that will round to 1.782. T-values should be rounded to 3 decimals. Z-scores 2 decimals, but t-values we want to round to 3 decimals to kind of make up for t being a little less precise than z. Here's another example. We want to know the area in the left tail where we don't want to know the area in the left tail. We want to know the t-score where the area in the left tail is 0.025. The degrees of freedom is 66. So again, there's your instructions using Desmos or the TI-84, and you should get negative 1.997, round to 3 decimals. Notice that the negatives and the positives follow the same pattern that our z-scores do. So very similar. Thanks very much.